In our previous video, we have related acid-base properties with electrochemical properties, and at the core of all that discussion there was the Nernst equation. The Nernst equation relates the cell potential that you measure with concentration of reactants and products. Another application of the Nernst equation is when we can measure concentrations of salts with limited solubility. And as you well remember, the KSP relates, and for example, for the salt that we're going to study now is silver iodide has limited solubility, and say that you do not know how much this value is, but so maybe you can measure the concentration of silver in a saturated solution of silver iodide by measuring potentials. So again, the connection between concentrations and potential that Nernst equation gives us is actually very, very useful. In this case, we are being asked to calculate the KSP, the solubility product of silver iodide. And maybe, well, if you go to the tables, the reduction potentials, you will see that these two values are fairly different, even though the reaction is the same. The reaction is the reduction of silver. The reduction of silver, depending on what compound is coming from, is very different. But what we're going to do now is to understand what exactly is going on here. If for reducing silver iodide solid, this is actually less spontaneous, we have to understand what is that it's actually reducing. And for that, we have to understand what this value here means. Silver iodide solid is in equilibrium with the ions, and let's say that this is saturated solution. So when we write this reaction from left to right, and the iodide goes away, what you're actually reducing is not the solid, is the little bit of silver that exists in solution with the solid. So one could think of this reaction as this reaction in which we have modified the concentration of silver plus, and therefore you can think of this number as the standard cell potential, and this one of the potential that is a result of modifying the actual concentrations. Let's do that. Let's apply this into this specific problem. So what we measure when we do not work at 1 molar solution, remember this is not 1 molar solution because it's a saturated solution. If we were to work at 1 molar, it would be 0.8 RT. I have 1 electron, F logarithm of what? Of products. This is a solid. Concentration of iodide over concentration of, and now this you would be done if you consider this as your reactants, but as we said, this would be the concentration of silver. And notice that, well, if we work at 1 molar solution of iodide, or regardless, even if we do not work, it would cancel out even if we were to put this concentration here. So we don't need to write it. It's just 1 over silver. So notice that this potential becomes so negative because this is not 1 molar. This is smaller than that because you have a saturated solution of a limited solubility solid. Therefore, by reducing the amount of reactants, you have a more negative potential. So for KSP, if we work at 1 molar solution of iodide, one can prepare 1 molar solution of iodide, but of course the concentration of silver will be different because it's a saturated solution. This is 1 molar. If we find the concentration of silver, we will have found the concentration of, we will have found the KSP. Not a straightforward solution. The most important part of all this video is to be able to read these lines and to understand that the reaction is the same. It's just that the concentrations of reactants and products are not the same when you have a solid of limited solubility. So let's find the concentration of silver in this saturated solution. Why is it saturated? Well, because we actually have 1 molar solution of iodide, there has to be a much less concentration of silver. Therefore, this will be negative 95 is equal to negative RT divided by F, logarithm of 1 over silver, positive, positive. Okay, and now actually I'm going to continue on this side. So 0.95 times F RT, and what I can do is flip, like putting a negative 1 in here, and this negative 1 would go back here. So make sure you have your properties of logarithms. This will give you the concentration of silver, which at the same time, using this equation, is equal to the KSP. If you calculate this number, this will give you around 10 to the negative 16, which is pretty close to the KSP. Therefore, the take-home message of this video, I understand that it may be a little bit hard to see the connection between these two reactions, but it's a way for you to see that the Nernst equation can also be used to relate concentrations of solids with limited solubility and the potential. This is equal to the KSP.